Okay, so hello everyone. Welcome to today's talk. So today we'll have Zhewen to give us an exciting talk on the exploiting value characteristics for computing. And Zhewen is a fourth-year PhD student in the ECE Department at the University of the Wisconsin-Madison, advised by Joshua San Miguel. So her research focuses on power-efficient computer architecture. So her work has been recognized with the IEEE topic honorable mention, ISCA Best Paper honorable mention, ASPLOS Distinguished Artifact Award, and ACM SIGMICRO Student Research Competition Gold Medal. She is also a recipient of the Google Ph.D. Fellowship in 2025. So yeah, take it.
All right, thanks for the introduction. Hello, everyone. My name is Zhewen. I'm a fourth year PhD student at UW-Madison ECE Department. So today I'm happy to present you my PhD work. The title is Exploiting Value Characteristic for Efficient Computer Architecture. If you have question, make sure you speak up. That's fine to interrupt. All right, let's get started. Um, Today's computing system treat every bit the same. So they process and store bits blindly without knowing what the values actually are. But if you look closely, data isn't just random noise. So there's rich structure inside those bits. Some data are highly similar to each other and some repeat over and over again. My work turns that observation into a design principle called value-aware computing, where we build architectures that recognize and exploit data structures or like data characteristic to make systems faster, more efficient, and potentially more sustainable. So today I'm going to talk about two works that apply this design principle across the computing stack. So one of them is in memory hierarchy and the other one is in compute layer. So first, on the memory side of things, we observe that the data stored in caches have a lot of similarity, both within and across the cache lines. By pairing those similar lines and storing their bitwise XOR, we can catalyze compression by reshaping the data into a more compressible form. This is our XOR cache work, which received a Best Paper honorable mention at ISCA 25. Second, moving from memory side down to the compute side, we observe that in AI workload, we often process many repeated values. This is fundamentally because modern models use low precision data formats and large batches of data. So instead of recomputing the same thing over and over again, we can compute all the unique value once and then look up the results using time. So this will transform the traditional arithmetic into a value subscription and delivery paradigm. And that is Carrot, published in at ASPLOS and recognized at the IEEE microtopic honorable mention. So together, I hope by these two works, I will convince you that the data semantics can be a new axis for architecture optimization. We can build leaner and greener architectures by looking more closely at the data. So let's dive into our first work, which is XOR cache. So this work exploits value similarity in the memory, more specifically in the last level cache of the traditional CPU. Um, so the motivation is that today's computing system allocate a significant amount of resources to caching. The last level cache can occupy a substantial portion of the die area. So for example, as highlighted here in purple, AMD Zen 3 dedicates around 40% of its die area to its 32 megabyte L3. While large caches offer increased capacity, this doesn't always translate into improved performance. So a lot of research demonstrate that a majority of cache hits actually come from a small subset of lines. What's more, large caches often incur high latencies. Considering these factors, traditional large caches may not be cost-effective for future system, given their disproportionate performance and cost implications. So that said, computer architects have turned to efficiency optimizations. Cache compression is one of the promising line of research in this area. By exploiting redundancy within the cache data, these techniques reduce cache footprint, effectively achieving the performance of a large cache using a smaller one. So cache compression method can generally be classified into two categories, intraline compression and interline compression. Intraline compressors take advantage of redundancy within a single cache line, while interline compression exploit redundancy across multiple lines. Our work sits in between, exploiting the synergy between the two. At a high level, it performs a interline XOR compression, leveraging the redundancy from private caching and inclusion, which is common in today's cache hierarchy. When combined with other intraline techniques, it can further enhance compression ratio. So now let's dive in to see how our XOR cache works. We will see how it works by comparing it against a uncompressed cache. So conventionally, cache lines are inserted as is. For example, the line A and B here, we usually store them as separate lines in your last level cache. On a private cache miss on line B, the L1 on the right sends out its request to the last level cache. And the last level cache services the miss by sending the line B to L1. For XOR cache, when inserting line A, we actually try to find a similar line B here to perform a bitwise XOR with it. And the XORed line, A XOR B, is stored in the last level cache, allowing A and B to collocate in one physical slot. So we use the yellow dashed box to highlight the space saved by this interline compression. And with every line pair effectively collocate, the XOR cache achieves an interline compression ratio of 2. Also note that since A and B are similar to each other, the XORed line A XOR B ends up with many zeros in it, which means we can further compress it to a smaller size using intraline compression scheme. We highlight this intraline compression ratio or space saved using the orange dashed box here. And that's it for compression. Let's now see how decompression works when XOR cache services a miss on a XORed line. So suppose we have the same miss on line B from the private cache on the right. When servicing the request, when receiving the request, LLC forwards the XORed line A XOR B to the requester. So in this specific case, requester of B shares a copy of line A, so it reads out A to perform a bitwise XOR again to reconstruct B locally, and the miss is serviced. This is the high-level overview of XOR cache compression and decompression operations. Before we talk about its implementation, maybe let's zoom in a little bit to characterize XOR cache compression ratio, particularly how to find a good candidate to XOR with. So here we consider 3 cache compression baselines, base delta immediate or BDI, bit plane compression, and thesaurus. Those are all published in prior works. We profiled their compression ratio by analyzing the LLC snapshot when running representative benchmarks. So this is the first set of bars. So we look at if we randomly select every 2 lines to be XORed, like how does the compression ratio look like? This corresponds to the second set of bars. As we can see, we will achieve some compression ratio boost but can we do better? As we have discussed, we want a similar line pair A and B to be XORed together. We want a similar pair of A and B to be XORed together. Let's see a concrete example here. So here are two sample lines from running the body track benchmark. They are almost identical with just a few bits difference. When we XOR them, we end up with a more compressible pattern with many zeros, which means we can further compress this line A XOR B. So in this specific example, A and B using intraline compression, I think in this case is BDI alone, can be compressed down to 16 byte each, so making them 32 byte in total. Whereas when combined with XOR compression, they can be aggressively compressed down to 8 bytes, showcasing XOR's ability to work as a catalyst for compression. So with this insight, we consider a pretty ideal configuration where we allow the XOR cache to search for the best candidates for a line within its set, which we call ideal set. With this configuration, our compression ratio improves from the previous random XORing configuration. So if we further allow a line to search at a larger scope, in this case, search for its XOR candidate across the entire bank, which we call ideal bank scheme, we will achieve even higher compression ratio. So that's the fourth set of bars here. So this boosts baseline compression ratio by more than 2x. So backed by these results, we showed that XOR compression has great potential as a catalyst for boosting compression. Now, let's continue our discussion of XOR cache architecture. We have showed that XOR cache inserts XORed line as opposed to individual lines in the last level cache. This is handled by XOR cache's compression algorithm. And on access, the last level cache forwards the XOR line to a private cache to reconstruct the missing line. This is handled by XOR cache's decompression flow. Note that we have showed here is just one of the three cases of decompression. We will talk about the other two shortly. Finally, we will show that XORing is not always possible. Note that unXORing is fundamentally different from decompression, in that decompression happens on LLC hits, and the lines in LLC can stay as XORed with no problem. Whereas unXORing refers to the cases where we need to unXOR a pair to keep all of them recoverable at all times. We will illustrate these three things next when we discuss XOR cache coherence support. Before I move on, any questions so far? All right. So here's the stable state of the MSIP protocol for the LLC, and I, S, and I, M are the stable states, as you may see in your Intro to Computer Architecture course. So besides I, S, and M states, I have another state, which is S0. This is a special shared state with an empty shared list. So we don't actually, for implementation, we don't need to distinguish S0 and S. This is just showing here for clarity of presentation. So a line in LLC can only possibly XOR when it's an S or S0 states, highlighted in gray here. Note that a M state line is potentially stale in LLC and has a more up-to-date copy in its private cache. So this forbids reconstructing the original line, so we cannot XOR M state lines. If we draw out all the transition or the edges, this is for baseline MSI. We have all these edges in there. And for compression, it will happen on those insertion edges, basically transitions within and into the XOR states. So for example, on edge number one, when servicing a LLC miss, the line transition from I to S, and this line can find another line to collocate. And on transition number two, when a private line write back its dirty line, this line can also try to XOR with another. And on transition number three, when LLC downgrades a line from M to S, the up-to-date line from the private cache similarly can write back to LLC, and it can also XOR with others. Next, when XOR cache services a read request to an XORed line, it needs to decompress it. We highlight all the related transitions in gray. These are transition number 4 and 5. They are all related to servicing the getS request from the XORed states. So as mentioned earlier, we have three cases of decompression. The first one is local recovery, and this is exactly what we have covered so far. To recap, the private cache on the right detects a miss on line B, so it sends out requests to the last level cache. The last level cache forwards the line AX or B to it. B's requester itself has a shared copy of line A, so it can recover B using it. So to sum up, line A is in S state. B can be S or S0, and the requester for B has a shared copy of A. And in the second case, we call it direct forwarding. The requester of B does not share the line A, but B has a sharer in its private cache, which is the one on the left-hand side. So the LLC simply forwards the request to the B's sharer, and this is handled in a similar fashion as any protocol that implements a forwarder state. So in our last case, remote recovery, line B has no shared copy in the private cache. Therefore, it is in S0 state in the last level cache. Also, B's requester does not share a copy of line A locally, but there is another private cache, which is the one on the left, that has a shared copy of A. So in this case, the LLC forwards its XOR line to it, it recovers B remotely, and then finally sends it back to B's requester. Note that the coherence protocol for XOR cache guarantees at least one in the XOR line pair has at least one sharer. This is entirely by design. Therefore, any request for an XOR line will follow one of the three cases that we covered here. So far we've talked about compression and decompression, and the last piece is on XORing. This is needed in an XOR cache to make sure that every line is recoverable. We will need to on XOR a pair if any of them upgrade to M states. This corresponds to transition 6 and 7. We need to on XOR if neither of them have a shared copy in the private cache. And this case corresponds to transition 8 on the last put as request. And lastly, we need to on XOR when one or both of them are evicted. This is related to transition 9 and 10. So I won't be able to cover the implementation of the on XORing and its implication on deadlock freedom, but all the details are in our paper. All right, XOR cache detailed organization are shown here. So we adopt a decoupled tag data organization. Note that we also have a special structure called map table shown here on the right. So at a very high level, the map table works as a hash table and is used to identify similar lines that should be XORed together. It is indexed using a map function with line data as input, and each entry stores a tag pointer pointing towards the standalone lines in the last level cache. An XOR cache insertion flow is shown on the bottom, which is entirely off the critical path. Using the cache lines data, we first compute the map function to index into the map table. Recall that the map table stores all the tag pointers of the unXORed lines. And if the map table misses, this means that there's no similar candidate for now. So we skip XOR compression and insert its tag into the map table. Otherwise, on map table hits, it means there exists a good candidate as their hash function values, hash values match. So we would deallocate the map table entry and would read out the candidate's data and insert the unXORed line into the data array. Also, the details for map function design and XOR cache access flow are not included here, but all in our paper. So going to the evaluation section. So here's a quick summary of XOR cache evaluation. We use Gen 5 Ruby memory model to run full system simulation of multi-threaded, which are perfect and parsec benchmarks, and also multi-program workload using the Spec 2017 suite. We simulate a 4-core system with 3-level caches, and we sized our compressed LLC according to the profiled compression ratio. And we've seen that XOR cache can boost compression ratio by 23% on multi-threaded and 35% on multi-programmed workloads. And also on the cost side of things, XOR cache can reduce area by 1.9 over the uncompressed baseline, and it reduces power of the LLC alone by 1.92x, and it reduces the power of entire cache hierarchy by 1.46x. And XOR cache indeed has a slowdown, so a performance overhead of 2%, but summing everything up, it still achieves a reduction in EDP, which is energy delay product, by 26%. So this is a summary of our XOR cache work. We exploit the redundancy due to private caching and inclusion. We perform a XOR interline compression, which catalyze interline compression opportunities. So the evaluation results shows that XOR cache reduces LLC area by 1.9x, power by 1.92x, and energy delay product by 26%. Okay, that's it for our first work. And if there's any question, please speak up. All right, so I will move on to our second work, where we exploit value redundancy existing particularly in AI inference workload. And this is Carrots published in ASPLOS 24 and got IEEE topic honorable mention. So in recent years, in addition to the standard IEEE FP32 format, multiple low precision data formats have actually been proposed for machine learning. These low precision data formats, such as BF16 and FP8, incurs minimal accuracy loss and are becoming generally supported by the ML hardware. Note that FP8 has only 3 mantissa bits as opposed to 23 bits in FP32, which is usually an overkill for machine learning workloads. So the data being processed here are effectively getting smaller and smaller. Additionally, in batch processing scenario, many data are readily available for processing simultaneously. So given this trend towards lower precision and larger batch size, we identified that not all computations are mandatory in existing GEM architectures. Let's look at one example of the scalar vector multiplication. So if we assume there's a vector of dimension 1k, and the data format is int4, a single multiplication can only produce 16 unique results. Regardless, conventional GEM architectures still perform 1k independent multiplications, which end up being 64x more computation than what's actually needed. This is far from being efficient. So to bridge this efficiency gap, we identify there's opportunity um, where multiple parallel inputs can reuse one computed output, regardless of their input values. So we coined this paradigm as value level parallelism, or VLP for short. So we'll demonstrate this by continuing with our scalar vector multiplication example. Conceptually, we can transform the scalar vector multiplication into a series of scalar accumulations, and we refer to this as value reuse. With that, all the independent input can reuse this multiplication results as their outputs. And this is achieved by a form of subscription, which where each input read out its corresponding output depending on its value. Transforming this VLP concept into a concrete architecture. For implementing value reuse, we said that instead of the hardware multiplier, we're going to use an accumulator to transform multiplication into accumulations. And for implementing subscription, we convert all the elements in the input vector into a temporal-coded bit stream and use it as an enable signal to update the product register. Before diving into Carrot's implementation, let's actually look at how much opportunity we have for value reuse. So here we have, we show the per layer number of inputs per unique mantissa values for ResNet 50 and BERT. So each of them represents the vision and language models. So in the context of value reuse, the curve reflects the upper bound number of value reuse happening at each cycle. As expected, for both BF16 and FP8, there are uniformly many values, inputs sharing the mantissa values. So this demonstrates value reuse opportunity at each cycle. And let's see how carrots work. So here's a quick intro of temporal coding that I mentioned earlier, in which the data value is represented as the delay. So in this specific type of temporal coding, also called spike timing, value is encoded as a timing of the spike. So for this specific example, temporal coded bitstream for value 6 has a spike at cycle 6. This conversion from binary to temporal is achieved by a comparator and a counter. And once again, we show our multiplier-free scalar vector multiplication here. So as the first step, we would transform a single multiplication into a series of accumulations. Then we convert the input into temporal coded bit streams and use the temporal bits as enable signals. And finally, we can have many parallel independent structure like this. Each of them correspond to independent input. but they all share the same set of accumulation results. And then here is our overview of our concrete architecture. Our caret architecture at a very high level computes outer product of an input vector and the weight vector. And the memory hierarchy and peripheral logic mirror existing GEMS accelerators. Let's actually zoom in and see what caret PE organization look like. So recall from earlier slides, a PE column effectively implement a scalar vector multiplication, so the column is composed of a column of temporal converter and a column of PE. Note that they share a single counter for conversion and accumulator for weight accumulation. Those are at the top. And each row staggers, as shown in the pipeline diagram here. So the green block here shows the zoomed in view of a temporal converter. It contains the hardware that converts the mantissa bits into temporal coding. And additionally, all the hardware that pre-process special values. The yellow block shows the zoomed in view of a caret PE. As opposed to conventional GEM accelerator, so they will usually have very compute heavy PE. Caret PE here are very different. They're very simple and only implement subscription. So far we've focused on the column organization. Now let's move on to caret's PE row organization. So the temporal bit stream is propagated from left to right from the temporal converter to all the PEs in one row. So they form a generation subscription pipeline. Every bit seamlessly flow through this pipeline from left to right. So in the sequence diagram of the four, so they form a sequence of one generation stage and four subscription stage in each row. And here, the sequential bits from two input data are shown here. There could be two concurrent input values simultaneously in the pipeline though. Let's assume bit 3 and bit 2 are the spikes in the first and second data respectively. At cycle 7, PE4 output the product of the first input and the PE2 outputs the product of the second input. As shown on the right, we have two separate sets of hardware, including the OR gate and buffer for those two spikes. Additionally, we have more hardware for post-processing special values. And putting these all together, let's see how PE array is organized. Here we have 8 PE rows and 8 columns because we have 3-bit mantissa, and the PE pipeline depth has to match the length of the temporal bit stream. Counter values is propagated along the column dimension to each temporal converter. And similarly, accumulation results are propagated downwards to each PE. So in this way, each row staggers. And the temporal bit stream are propagated from left to right. In this way, the columns also staggers, forming a two-dimensional staggered pipeline. So far we've covered the design of temporal converter, single PE organization, PE column organization, and row organization. In the paper, we actually discuss more detail, including but not limited to accumulation, fast forwarding optimization for floating point numbers, special value handling hardware, including subnormal adjustments, product masking, and exponent expansion. And in addition, we also include a walkthrough timing example. And here's a quick recap of our evaluation results. As you can see, this is the cost breakdown. This is on the left. Two pie charts are the area breakdown, and on the right-hand side is the energy breakdown. You can see that carat PE, the composition of carat PE are very different from your traditional BSA, so the binary systolic array. And PE only contributes to 7% of the array area and 10% of the array energy. And the large, so this graph sweeps the batch size, and we um, measure the normalized throughput. As you can see, as large or as batch size increase, the throughput increases. The large batch actually exposes richer VLP opportunities, so Carat eventually um, surpasses all the other designs. And here we um, measure energy efficiency, which is throughput per array energy. And you can see that the orange bars are tallest, we achieves 1.23x and 2.17x array energy efficiency than your traditional binary systolic array, and RIS, which is another binary design that also leverage computation reuse. So here, so I won't have time to walk through this timing example. Yeah, so I guess that's it for this talk. In this talk, we went through two designs. One of them is XOR cache, which focus on value similarity in the memory layer, more specifically focusing on compression in the last level cache. And also in the second work, we exploit value redundancy in the AI inference workload compute layer and identify opportunity to reduce redundant computation. Right? With that, I'm happy to take any question.
Okay, great. Thanks for the talk. So any question from the audience? So Daniel, you're in the audience, right? So any questions? Yeah, maybe something wrong with the microphone. Okay. Yeah, then if no questions, maybe I can ask a question.
Sure.
So what do you think, for example, for the value level parallelism, what do you think, for in the future, what do you think it's, application in like a larger scale AI machine learning workload? Or what do you think is a, you know, potential future optimization of the current architecture?
Right. We did actually brainstormed like future direction for this idea because on the high level it's an abstract conceptual idea. So you could potentially extend this to um well, it has to be other concrete architecture, but the idea is similar. So the potential direction that I'm seeing is more like a compiler side of things where if your compiler can recognize there's redundancy or like optimization enabled by value parallelism, um, maybe compiler could say something to guide the architecture or either novel architecture or existing architecture. To basically, because we have this chain with this specific work, we have the accumulator chain. But there could be more diverse chain where you have that opportunity of reusing prior results of your computation.
Okay. Yeah, cool. That's a pretty cool idea to explain architecture concept towards the compilation process. Yeah,
I have
so
a question.
oh, go ahead.
Sorry. Um, considering the architecture for the VLP array, um, what is the current bottleneck? What did you find as like the current bottleneck for the scalability of Caret?
Yeah, so I showed a lot of examples on the scalar vector multiplication, but when you actually stack this into like a jam operation, there's a huge bottleneck in the accumulation process, in the actual product accumulation process. So that fundamentally limits the scalability of this particular work. I think the reason was that we also identified this that Gem is not the perfect or the killer app for this. Yeah, so the answer is that we found like a huge bottleneck in product accumulation.
Okay, and to follow up on that, what do you find as the limiter um, for same scalability, but for the area?
Oh, you mean the plot here?
Sure. Yeah.
Yeah, so you can see the for either for area and energy, the plot looks similar, but there's a lot of red area, which is more than half of the entire pie chart. So that's the accumulator that I said earlier.
Do you see similar percentages as you look at larger array sizes?
Um, yeah, so definitely if you increase like the number of rows in your array, but accumulator is more like a parole thing, so it scales at a similar rate with your row size, and it's hard to scale like column wise because that depends on the mantissa width.
Mm-hmm. Okay. Thank you.
Oh, yeah, I saw a question in the chat. So if you are not able to speak, you can just type your question in the chat, okay? So the question is, why did Keras see increase in the throughput for larger batch sizes versus the RIS?
Okay, let me go to that plot. I think it's basically more higher utilization of your carrot array. So yeah, it's more like the utilization. They should all have similar peak throughput, but carrot has better utilization.
Yeah, I mean, if I remember correctly, the problem with the RIS is that it's reusing a certain dimension of the network, I mean, of the matrix convolution. And when you scale it up, uh, that specific dimension does not scale up. So you will see a diminishing return when you are increasing the batch size.
I see. So it's saturating pretty early on.
Yes, it's saturated early. Okay. Uh, maybe one last question. If no questions, then I think that's the end of today's talk. Thank you everyone for joining, and also thank you, Joven, for sharing the research with us. Very exciting research, and I will see you in the future. And of course, I will upload the video to YouTube and share it with everyone.
Thank you.
Okay. Yeah. Have a good night. Thank you.
Bye.
Bye.